So students, good evening all of you. So can you all hear me? So please do type in the chat box. Suyenda, well, so can you see the screen clearly and can you all hear me? Hello Suyenda, Tangavelan, Tanigai Velan. Okay, sorry. Yeah, I hope you people can hear me, correct? And you can see the screen clearly. Yes? Okay. So fine. Let us. So please tell me, sir, can you all see the screen clearly and can you all hear me? Yeah, I hope you can do that. Fine, Shubha. So let us attempt to solve this questions basically on all the topics that we have covered so far. So basically we have covered 5 topics as of now. So we have covered basic identification of fluid and we have seen the discrimination of fluid versus solid. Then also we have seen the Newton's laws of viscosity, and then in the third lecture we have seen the classification of fluids and compressibility, and also we have seen various cases of Newton's laws of viscosity, and of course we have also seen surface tension, correct? So we have seen what is the pressure difference between, yeah, fine. So we have seen what is also the pressure difference between different different fluid bodies, basically pressure difference within a bubble, pressure difference within a soap liquid droplet, and also pressure difference within liquid jet and all, correct? So shall we all solve some previous gate questions on this? So I have put some 20 questions today. So can we all solve them? So please try to solve. So please try to respond in chat box. So please do type in the chat box. Can you all hear me? And I think you can't read the comments in landscape mode as of now. So please follow this portrait mode, and so please tell me. Okay, fine, good. So let us go for the first question straight away. So see here, this is our first question. So let us try to read the first question. Two immiscible. So what is the meaning of immiscible? They can't mix each other, correct? So two immiscible, incompressible, viscous fluids. So these two words have to be identified. Immiscible and incompressible means the density doesn't change, and of course these two fluids which are here, they cannot mix. I hope the video is playing, correct? You need to click on the play button, Tanigavalan. Okay, fine, good. So see here, these two fluids are immiscible and incompressible, having same densities. So these two fluids have same densities basically. So if the density is taken as rho, then these two fluids have the same density rho, but different viscosities. Of course you can see clearly here, there is mu1 and mu2 which is denoted here, are contained between two infinite horizontal plates. So these infinite horizontal plates, of course parallel, 2 meters apart as shown below. So you can see clearly the difference between the gap in between these plates is 2 meters, and it's a horizontal gap, and the plates are extending infinitely. The bottom plate is fixed and the upper plate moves to the right. So this means the bottom plate is fixed. You can see clearly here, the bottom plate is getting fixed. So if the bottom plate is fixed and if this is moving right with a constant velocity of 3 meters per second. So this velocity of this plate is 3 meters per second, correct? This is 3 meters per second with the assumptions of Newtonian fluid. So assumptions of Newtonian fluid is valid, which means we can apply the Newton's law of viscosity, and of course if the velocity profile is taken linear here, so then you can apply this. Tau is equal to mu times of du by dy. This is what you can apply always, correct? Now see carefully. So with the assumption of Newtonian fluid, study and fully developed laminar flow with zero pressure gradient in all directions. So basically there is linear velocity profile, okay? So zero pressure gradient is what they have given, so there is linear velocity profile, and assuming zero pressure gradient in all the directions, the momentum equation simplifies to. So basically this is the relation between velocity and the y coordinate given. So you can see clearly here, this is y. So if this is x coordinate and if this is y coordinate, then they have given you the velocity variation with respect to y coordinate in this form: d square u by dy square is equal to 0. If the dynamic viscosity of the lower fluid is mu2, is twice that of the upper fluid. So mu2 is equal to 2 times of mu1. This is what we have here, correct? So mu2 is equal to 2 times of mu1. Then the velocity at the interface, round off to 2 decimal places, is dash meters per second. So basically they are asking you what is the velocity of this interface of the two fluids, correct? Definitely this is a common layer between both the fluids. So definitely this layer will be having some velocity whenever this upper plate is being moved at 3 meters per second. So they are asking you what is the velocity of this interface. So did we collect some data from the question and can we solve this? Yes or no? So please tell me, did we collect data from this question? Now let us attempt to solve this. The one thing that you have here is d square u by dy square is equal to 0. So let us write that. D square u by dy square is equal to 0, and this is the differential equation that's relating velocity with y direction, correct? So if you want du by dy from this du by dy is nothing but a constant, because only in case of this du by dy we are getting a constant, this d square u by dy square can be 0. So just if you integrate this once again, you will get, let us suppose if this is c1, u is equal to c1y plus c2, which means this is a linear profile, correct? So this is a linear velocity profile. This is a linear velocity profile. Now, if this is linear velocity profile, look, in this figure, definitely if you try to plot the velocity variation, initially let us suppose if this is the 0 scale, then this plate is moving at 3 meters per second and this is the stationary point. But it can't be a straight line from here to here because there is difference in the fluids, correct? So after this interface, there is different fluid. So let us suppose if this is the linear variation, then let us suppose if this is the velocity, then this will be another linear velocity, okay? So if this is some velocity at the interface, then definitely we have some other velocity profile here. But of course, to maintain continuity, what should happen? This velocity profile of the upper layer and this velocity of this lower layer, both should be same at this interaction or interface. Can you all identify this? So please do respond, please do type in the chat box. Can you all understand that whenever these two fluids, means if this bottom plate is fixed and the top plate is moving, and if this is the interface layer, then the bottommost layer of this first fluid and the topmost layer of this second fluid should have same velocity, and that's nothing but the velocity of the interface, correct? Hi Jansi, so please try to respond. Can you all see this? Will you all agree with me that if I say this is the velocity profile, this is how something it should look like? Can you all understand this? Yes or no? So please do type in the chat box. Correct? Yes. Correct? All of you, whoever is on live, so please do respond. Yes. Correct. So if this is the case, look, I am trying to develop something. If this is the interface and if this is the fixed plate and if this is the plate that is moving, then if you are having a velocity interface, like if this is 0 and from here we have, let us suppose, some other linear profile. Okay, so this is linear and also this is also linear. Now, see carefully. Definitely on this interface, we have two shear stresses that are acting. And what are they? Let us try to identify that. Whenever this interface is moving in the, having some velocity in that direction, there will be some shear stress because of this lower layer of this fluid, and also there will be some shear stress because of the bottom layer of the top fluid, correct? So if this dynamic viscosity is mu1 and mu2, there will be shear stresses tau1 and tau2 which will be acting towards left, and of course, sorry, this won't be left because see here. Yes, so since this layer is moving at a more velocity as compared to this, this will be in this direction, but of course the shear stress due to the top layer will be in this direction, correct? Yes, so if this is the case, so if you call this as tau1 and if this is tau2 and if this is dynamic viscosity mu1 and mu2, then definitely if this layer of fluid is moving at constant velocity v, then you have your tau1 is equal to tau2, correct? Means basically areas are same on both sides, so the force acting or pulling this interface towards the right by the upper fluid should be equal to the force that is applied by this lower fluid on this interface to pull it back, correct? This should happen. So if this is the case, since you know area is common on both sides, tau1 should be equal to tau2, which means mu1 du by d1. Du by d1 is nothing but c1, correct? C1, or you can write here, let us suppose if this interface velocity is v, then if this is 3 meters per second and if this is 0, then you can write velocity gradient in the top portion, which is 3 minus v divided by this clearance. And how much is this clearance given? You can see clearly, if this clearance is 1 meter, then this is also 1 meter, correct? This is 1 meter and this is also 1 meter. So 1 mm, of course, mm or meters. This is 2 meters. So this is 1 meter. This should be equal to mu2 into the velocity gradient in this liquid is nothing but v minus 0 divided by 1 meter again. So this is what we have. So it's clearly given. This mu1 is 2 times of mu2. Correct? This is given here. We have this mu2 is equal to 2 times of mu1 is that. Let us read. The dynamic viscosity of the lower fluid mu2 is twice that of the upper fluid. Then it is not. Then this is not this, but mu2 is equal to 2 times of mu1. Correct? So in place of mu2, we can write 2 mu1, which means you can cancel these two terms and you can write 2 here because mu2 is 2 times of mu1, and this 1 meter gets cancelled on both sides. So this implies 3 minus v is equal to 2v, and you can write 3 is equal to 3v and v is equal to 1 meters per second, which means the velocity at the interface is 1 meters per second. Is that clear to all of you? Is this clear to all of you? So please do type in the chat box. Can you all understand how these forces should be equal? Because you know, this layer is moving at a lower velocity as compared to the upper layer. So this upper fluid will try to pull this layer towards this. So the direction of force or shear stress that I have written here, I have put it towards right. But of course, the bottom fluid is moving a bit less than the speed. So this bottom fluid tries to retard this upper layer at the interface. Correct? So please do respond. Please do type in the chat box. So the answer of this question is 1 meters per second, and you can clearly see the range given is 0.98 to 1.02, which means 1 is within this value. Correct? Yes? Fine. Okay. Look here. Second step, how did we write? Tau is nothing but mu into velocity gradient du by dy. You know this. So if you see, this is the linear velocity profile. So the difference in the velocities between the upper fluid is, this is moving at v and this is moving at t. So 3 minus v is the difference in the velocity, and this 3 minus v difference in the velocities is occurring within a gap of 1 meter. So that's how I have written 3 minus v by 1 meter. Similar is the case here. Okay. Fine. Okay. So let us go for the next question. So this is one question that came in GATE. So in recent years, of course. So see here, a solid block of 2 kg mass. So definitely it's also given here. The mass of the block is 2 kg. Correct? Then, yes, I hope all of you are doing good. Correct? So let us read the question. A solid block of 2 kg mass slides steadily at a velocity v. So this is sliding at a velocity v, which is also given here in the bottom direction, along a vertical wall as shown in the figure. Okay. A thin oil film of thickness h is equal to 0.15 mm. I think there is some correction here. Yeah. This is 0.015. So this should be 0.015. Okay. This is 0.015 mm. Fine. Provides lubrication between the block and the wall. So there is some block and also there is some impermeable wall. What is the meaning of impermeable? There can't be any viscous fluid which is coming through the pores of this wall. Correct? So it is impermeable. So there is some impermeable wall and also there is some block sliding. Okay. A thin oil film of thickness h is equal to 0.015 mm provides lubrication between the block and the wall. Okay, fine. The surface area of the face of the block in contact with the oil film is 0.04 meters square. So this sentence has to be corrected. The surface area of the face of the block that is in contact with the fluid is 0.04 meters square. So basically, if you take a plane which is perpendicular to the board, then this area which is in contact with the fluid is 0.04 meters square. The velocity distribution within the oil film gap is linear as shown in the figure. You can see there is some linear velocity variation here. So the velocity variation is also linear. Fine. Is linear. Okay, fine. As shown in the figure. The dynamic viscosity of the oil is 7 into 10 power minus 3 Pascal second. So this dynamic viscosity of this oil is also given. So mu is also given. Then an acceleration due to gravity can be taken as 10 meters per second square. Okay, fine. Neglect weight of the oil. So this weight of the oil is neglected. The terminal velocity of the block is. So for such cases, I have given you some expression for the terminal velocity. Correct? So they are asking you what could be the steady state velocity or terminal velocity of this block whenever this block is sliding along this oil. Correct? So see carefully. Whenever we are having small gaps, then definitely this velocity profile is linear, and that's what they have also mentioned in this question. The velocity profile or the velocity distribution is linear. So can we apply Newton's law of motion? Left side of the board is not visible, Akhil side. Is it? Is it happening in the app? Okay. Is that happening to all of you? Okay, I think some portion is getting cut off in the app, correct? Okay, fine. Okay, so let us, okay, for this time, let us read the data and let me give you the key points. So if you see, mass of the block is 2 kgs, correct? So that means what is weight? It's given weight of the block is nothing but mass into acceleration due to gravity, and acceleration due to gravity is measured as 10 meters per second square. Yeah, it's not visible a bit. Yes, okay. So we'll make sure that this gets shortened for the next time, because I think, can we do something even now? Let us try to do this. Okay, but I think we can't do that. Fine. Okay, for the time being, I'll read the questions so you can respond accordingly. Okay, I'll read the complete question. Okay, so this weight is nothing but mass into acceleration due to gravity, which is 20 meters per second square. This is weight, so 20 newtons, correct? So 2 kgs into 10. So 20 newtons weight is falling. Then the velocity profile is assumed to be linear. Dynamic viscosity of the oil is given. Mu is equal to 7 into 10 to the power minus 3 Pascal second. And acceleration due to gravity is also given. So they are asking you terminal velocity of the block. Look carefully. They are asking you for the terminal velocity of the block. Now, when this block is sliding in this direction, definitely the weight will start acting downwards, correct? If weight is acting downwards, but still if the block is moving steadily, that means there is some force in this direction. And what is that force? Definitely the viscous force offered by the fluid, correct? So the viscous force offered by the fluid. So if the block want to move at steady state, definitely this viscous force and this weight, they should balance each other, correct? So let us say viscous force should be equal to W, and viscous force is nothing but shear stress into area in contact, which means tau is nothing but a mu times of du by dy. Its linear velocity profile, and this gap is also given 0.015 mm. So the terminal velocity V divided by the gap 0.015 mm. So that can be written as 15 into 10 power minus 5 in terms of meters. Mu du by dy into area. What is the area that we have here? 0.04 meters square. So 0.04. This should be equal to mu into velocity gradient. This is the shear stress into this area. Should be equal to weight, which is 20. Correct? So let us write this equation in the next part. So mu into V by 15 into 10 to the power minus 5 into the area in contact is 0.04. So let us write this as 4 into 10 power minus 2. 4 into 10 to the power minus 2. And what is the value of dynamic viscosity? Let us substitute this even. So dynamic viscosity value is given 7 into 10 to the power minus 3 Pascal seconds. So 7 into 10 to the power minus 3 Pascal seconds. Okay, this is the SI units. So this should be equal to weight of the block, which is 20. So from this equation, can we find V? Yes or no? So please respond. Can we find V from this equation? Can we find V from this equation? Yes? Can we find V from this equation? So please tell me how we can find. Let us do some simplifications. So if you perform some simplifications here, this 10 power minus 2 and this 10 power minus 5 and this 10 power minus 3 cancels together, correct? And this 4 can be cancelled with this 5. So your V is equal to 5 into 15, which is 75 divided by 7. So 75 divided by 7 is nothing but, if you cancel this 10 times, because it's 70 and there is 0.5, so 10.7, then 49, so 10, so 10.71 around. So 10.71 meters per second is the terminal velocity of the block, correct? So terminal velocity of the block is equal to 10.71 meters per second. Correct? So this is 10.71 meters per second. Let us check the options if we have. Okay, we don't have options, but it's a numerical answer type question. So 10.71 is the correct answer. And if you see the range, correct answer given in GATE examination is 10.6 to 10.8. So obviously 10.7 is in between that. So correct to 1 decimal place is what they have asked. So 10.7 could be the answer. And 10.6 to 10.8 is the range. So are you all clear with this question? So please tell me, are you all clear with this question? Are you all clear with this question, beta? So please type in the chat box. And I think your phone number which you have registered with is getting displayed somewhere in between here and there. So I think it's a good thing. You're getting dynamic watermark. Okay. Is that clear to all of you? Yes. Very good. So let us go for the next question. Fine. Okay. This is 10.7. So this is the question. So consider fluid flow between two infinite horizontal plates which are parallel. The gap between them is 50 mm. So there are two infinitely parallel horizontal plates. So there are two infinitely parallel horizontal plates and the gap between them is 50 mm. Correct? This is what they have given you. The gap between them being 50 mm. So this is what they have given you. The gap is 50 mm. So this difference is 50 mm. Fine. Now the top plate is sliding parallel to the stationary bottom plate at a speed of 3 meters per second. This as sentence gives us a lot of data. the top plate is sliding parallel to the stationary bottom plate. What do you mean by stationary bottom plate? This bottom plate is again fixed. Correct? This bottom plate is again fixed. If this bottom plate is fixed, this velocity is 0 meters per second, of course, and it is the top plate is sliding at a speed of 3 meters per second. So this velocity u is in this direction, let us suppose. So this is 3 meters per second. Anyhow, this is good. Then the flow between the plates is solely due to the motion of the top plate. Of course, so the flow between plates that's happening is because of only the movement of this horizontal plate. The force per unit area magnitude required to maintain the bottom plate stationary is dash. So see here, definitely this bottom plate has to be stationary. So what is the force per unit area of the plate that you need to apply? Look, definitely why this plate is stationary? Why this plate is stationary? Because of the shear stress acting on this plate, correct? So this force per unit area, this is nothing but shear stress, correct? Shear stress that's acting on the plate is nothing but force divided by area. And as per Newton's laws of viscosity, you know that this is equal to mu times du by dy, and of course this du by dy is at y is equal to 0. If you take this as your x coordinates and this direction as your y coordinate, then definitely this is mu times of du by dy at y is equal to 0, correct? And this is a very small gap, so definitely we can, nothing is mentioned about velocity profiles, so you can take the velocity variation is linear. So let us suppose we have linear velocity variation. Okay, so let us suppose we have linear velocity variation. So this is linear velocity variation. So this is 3 meters per second. So if you want to have this shear stress value, then mu can be written as viscosity of the fluid mu is equal to 0.44 kg per meter second. I clearly told you during the conversion, yes, it is fixed, and I clearly told you during the conversion 1 Newton second per meter. 1 Newton second per meter square, Pascal second basically. This is equal to 1 kg per meter second. I have shown you this conversion. Do you all remember? During the conversion of units of dynamic viscosity, I have shown you the SI unit, 1 SI unit of dynamic viscosity is nothing but 1 kg per meter second. Correct? This is what I told you. So this is equal to, since this is in SI units, means the value doesn't change even in SI units, we can directly substitute 0.44. That is nothing but 44 into 10 to the power minus 2 into du by dy. So what is the velocity gradient? Within a gap of 50 mm, the velocity is getting from 0 to 3 meters per second. So the gradient can be nothing but 3 minus 0 divided by, this is 50 mm. So this 50 mm can be written as 50 into 10 to the power minus 3 meters at y is equal to 0. But of course, since this is the linear velocity profile, the velocity gradient is same at each and every point. Okay. So this is the value which we need to calculate, the force per unit area. So if you perform this calculation a bit, 10 power minus 2 and this 10 power minus 3 and this 0 gets cancelled off, correct? So 44 into 3 is nothing but 4 3s are 12 and this is 132 divided by 5 is left with us, correct? So if you perform this calculation, this is 26.4 because 5 into 26 is nothing but 130 and because of this 2 we have something like around 26.4, correct? So of course, what are the units? Since we are dealing everything in SI units, this is nothing but Newton per meter square, correct? So basically Pascals. So 26.4 and what did they ask you? In dash Newton per meter square. Okay, so this is the value in Newton per meter square, 26.4. And what is the official answer given in GATE examination? 26.3 to 26.5. So 26.4 is the exact answer in this case. Correct? So are you all clear till this point? Are you all clear till this point? Okay, so I hope all of you are clear till this point. So basically the main intention is this velocity profile has to be linear, and of course this shear stress, shear stress is nothing but mu times of du by dy, and where our assumptions like Newtonian fluid and linear velocity profile make these two things mu and du by dy constant at any location or at any layer of the fluid. Correct? So whoever is on live, so please do respond. All of you. Shubha, Jansi, Suyendra, Indu and all. Mumana, Akil. So, okay, so all of you please be responding. Yes, Jansi, good. So let us go for the next question. Yeah, this is the next question. The difference in pressure in Newton per meter square across an air bubble. This word has to be made a note in this question. Air bubble of some diameter 0.001 meters immersed in water is dash. Of course, the difference in pressure in Newton per meter square across an air bubble of diameter 0.001 meter immersed in water. Surface tension is given to be 0.072 Newton per meter. Correct? So there is some air bubble. So inside there is some air, and this is also air. Okay, there is some air bubble. So if this air bubble is immersed in water, this air bubble is immersed in water. Correct? So this is some air bubble. So the difference in pressure across an air bubble of diameter, this is some diameter is given, immersed in water, whose surface tension is something. Now, please take carefully, this is immersed inside the water. This bubble is immersed inside the water, correct? So if the bubble is immersed inside the water, I told you that pressure difference is nothing but, in case of a bubble, 2 sigma into 1 by R1 plus 1 by R2, correct? In case of bubbles, we have seen yesterday. In case of bubbles, this is the case, correct? If this is the case of bubble, and of course this is a perfect sphere, then this delta P means the pressure difference is nothing but 2 sigma into, this is 1 by R plus 1 by R, which is 2 by R. Yes? But now, this is what I told you. Now, tell me clearly, can we apply this formula here? This is what I told you yesterday's class. So please tell me, can we apply this formula here straight away? Last class notes not uploaded? No, Suyanda, I have uploaded in the Telegram channel immediately. So please tell me, can we apply this formula straight away here? This is the one question that I want to ask you, because I told you this for the bubble, this is the formula. Yes, I do agree. Now, can we apply this? No. Very good, my friends. Because, why no? Look here, I will tell you why you can't apply here. When we were talking the other day about some soap bubble or something, this is one material and here there is air inside. So there will be some surface tension along this edges also, correct? But now if you see what is the substance here, this is air and there is only one interface of liquid and air, correct? There is no second interface, means this bubble is also a air bubble. So how many interfaces are there? Only one interface, which means you are not supposed to apply this 2 in this case. If this air bubble is normally at some other location, means generally if this is some soap bubble or some other thing, and if this is in air, then definitely have 2 interfaces of air and soap bubble. But in this case, you can see clearly there is only one interface, because this is mentioned as an air bubble. So if this is an air bubble, then you have only one interface of fluid and gas, correct? So we can't apply this 2 directly here. So what is the pressure difference? Delta P actual in this case is equal to sigma times of 1 by R1 plus 1 by R2. Are you all clear why we are applying this formula? Because this is an air bubble, and if this is an air bubble, then definitely this film is also air, and this interface, which is inside interface, can't be treated as actual interface of surface tension, because both the materials are same, and there is only here we have air, and of course on the outer side we have a liquid. So there is only one active interface that's participating here. Is that clear? So if you solve this, we have 2 sigma by R, and that can be written as 4 sigma by D, of course. And what's the value of sigma and D given in this case? 4 times of sigma is 0.072. So that can be written as 72 into 10 to the power minus 3 divided by, and what's the value of diameter? 0.001 meters, which is 10 to the power minus 3 meters. So if you cancel this 10 to the power minus 3 and 10 to the power minus 3, this value is 4 times of 72, so which is 288. And what are the units? Pressure difference, of course, so newtons per meter square. So that's what even given, 287 to 289 is the official gate key. Are you all clear why we can't apply this 2 here in this case? Because number of interface are only, means number of active interface that induce some surface tension is only 1 in this case. Are you all clear till this point? Yes? Are you all clear till this point? So please do type in the chat box. I hope you guys are clear. So let's go for the next question. Fine. This is one question. A lightly loaded full journal bearing has a journal diameter of 50 mm, bush bore of 50.50 mm and bush length of 20 mm. Means, see here carefully. There is one journal diameter and I have shown you this case, the journal case. So let us suppose this is some bush bore. Then within this there is some shaft that will be rotating, correct? And let us draw the shaft here. Okay, so this is some shaft and this is your axis. This is your axis. So this will be your shaft. Okay, and what is present in between them? There is some always there will be some viscous oil that will be present in between them, correct? So there is some viscous oil that is present in between them. There is some viscous oil that is present in between the shaft and the journal. And what happens generally? This journal is something fixed, correct? So if this journal is fixed, this journal is fixed, and of course there is some viscous oil in between these two. Fine. So see here, if you try to see carefully, this journal will be fixed. This journal is fixed, correct? Okay, fine. This journal is fixed, and this shaft is rotated at some angular velocity curve, of course 1200 rpm. Okay, so this is rotated at 1200 rpm, and that means your omega is equal to 2 pi n by 60. So 1200 divided by 60, which is this is 20, correct? So this is 40 pi. Omega is equal to 40 pi radians per second. 40 pi radians per second. Fine. The shaft diameter is 50 mm. So this shaft diameter which is here is 50 mm. And you can see carefully, the shaft is rotating about this axis, and every point of fluid solid contact. Every point of fluid solid contact. This is at an equidistant from this reference, correct? So we need not do any integrations, correct? Fine. This is the case. So if you want to write the expression for if the rotational speed is something, the power loss in what will be? So power loss, power is nothing but torque into angular velocity, correct? So how we can write this torque? Torque is nothing but viscous force into the radius at which this viscous force is acting, and at every point this viscous force will be acting on the periphery of the shaft, and that is half of this distance, correct? So which is d by 2 into omega. This is what we have. And what is this viscous force? Viscous force can be written as shear stress into area of contact. So that is nothing but shear stress into what is the area that is in contact with this fluid and solid, which is nothing but the circumferential area of the shaft, which is pi dl. Pi dl into d by 2 into omega, correct? And of course, how you write this tau? Assuming this to be a Newtonian fluid, tau can be written as mu into du by dy. Now, what is this du by dy? Look, what will, here, this is a fixed thing. So definitely, if you try to draw, there exists some velocity profile here, correct? There exists some velocity profile, and this velocity increases linearly in this case, because this point has zero velocity, and this velocity of the point on the shaft will be equal to v is equal to linear velocity is equal to r times of omega. So this is d by 2 times omega in this case, correct? So if you write the velocity gradient, mu into velocity gradient will be d by 2 times omega divided by the clearance. Clearance is nothing but this gap. Let us suppose this is c for the time being. Okay, if this is the c, then this is the velocity gradient. Mu into velocity gradient gives you the shear stress into pi dl into d by 2 into omega. So we have all the things. So let us write a formula for this. P is equal to pi. We have written this pi. So mu pi mu, then 1 2 3, there are 3 d's, so d cube into there is one l into how many omegas are there? There are 2 omegas, so omega square divided by 2 into 2, 4c. We have 4c in the denominator. So this is the formula that is with us. Now what? Let us identify the values. Pi is a constant anyhow. What is the value of mu? It's given average viscosity of the liquid lubricant is 0.3 Pascal second. So if this is the case, you have your input as mu is equal to 0.3 Pascal second. Then mu is with us. What about d? Diameter of the shaft is given 50 mm. So diameter of the shaft is 50 mm. So if you convert in meters, 50 into 10 power minus 3, which is equal to 5 into 10 to the power minus 2 meters. Okay, this is known. Then what about length of the journal? Length of the journal is also given, and bush length of 20 mm. So bush will be very small in length generally. So 20 into 10 to the power minus 3 meters. This is what L. Then what about omega? Omega we got 40 radians per second. So omega is equal to 40 radians per second. This is also known to us. Then what has to be known? See, clearance. Look carefully. The journal diameter of 50 mm and the bush bore of 50.5. Look, if this is totally of 50.5, then this clearance should be equal to half of the difference between bore and shaft diameter. Correct? So that will be nothing but 25.25 minus 25, which is C value should be equal to 0.25 mm. That can be written as 25 into 10 to the power minus 5 meters. Let us substitute all these things. I hope all of you are clear till this point. How we have obtained all these data points. Correct? So if you have obtained all these data points, let us substitute. Pi into mu. What about mu? Mu we have seen just 0.3. So 3 into 10 to the power minus 1. This is also fine. Into then d cube. What about d? D is 5 into 10 to the power minus 2. So d cube will be 125 into 10 to the power minus 6. This is what we have, d cube. Then in terms of L, L is nothing but 20 into 10 to the power minus 3. So 20 into 10 to the power minus 3 into omega square. Omega is 40 pi. So square of this will be 1600 pi square. 1600 pi square. This whole value divided by 4 times of clearance. What about clearance? 25 into 10 to the power minus 5. So 25 into 10 to the power minus 5. Let us calculate, let us substitute and calculate this value. If you calculate this value, let us see how much we will be getting. Okay. So basically, if you see, this 100 can be cancelled by this 4 and 25. Correct? Similarly, what can we do else? This 10 to the power minus 1 and 10 to the power minus 6. Okay. So if you see this 0, this 10 to the power minus 6 and this 10 to the power minus 5 can also be cancelled. So what are the terms that we have in cut short? 3 into 125 into pi and of course into 2 into 10 to the power minus 3. So basically 2 into 125 is 250, 2 into 125 is 250 and 3 times of 250 is 750. So 3 times of 250 is 750. So 750 into pi square into pi. So 750 into pi cube into 10 to the power minus 4. So 750 into pi cube into 10 to the power minus 4. Let us calculate this value and the value is in watts. So let us calculate this value 750 into pi cube into 10 to the power minus 4. Let us calculate this. Let us take the help of a virtual calculator which you will be having the same calculator in GATE as well. So let us take the help of this calculator. So what is the value that is with us? 750 pi cube into 10 to the power minus 4. So see carefully. And using this virtual calculator is really important in GATE. Okay. Because if you compare All India first ranker and All India rank 100, the difference will be only this virtual calculator. Okay. So please take care of this. So 750 into pi cube. You can see pi here and cube here. So pi cube into 10 to the power minus 4. So into 0.0001. So if you calculate this value, 2.325 watts. So if you see 2.523, we don't have the value somewhere. So did we mess up? 1600. Okay. What about this 16 here? This 16 is also still present. So 16 times of this value. Correct? So into 16. So this value is nothing but 37.2. Okay. So this is nothing but 37.2 watts. So 37.2 watts. And if you compare the answers and if you check the answers, the most appropriate answer is 37 because the final answer is 37.2. So 37 watts is the correct answer and you can see the official gate key is also answer A. Is that clear to all of you? Yes, clearance is present on both sides, but that's the reason why I am multiplying with pi dl here. Here I am not multiplying with pi r by 2l. Okay, pi dl gives the complete circular look. If this is a circle of diameter d, then pi dl will give the complete area of the shaft. Okay, which means we are taking into consideration the complete area of fluid and solid contact. Is that clear? Is that clear to all of you? Please respond. Is that clear? C value, explain again, sir. Book here, we are not. No issue. Look here. This total diameter of the bush. This total diameter of the bush is 50.5 mm. You can see 50.50 mm. 50.50 mm. If this total dimension is 50.5 and this is 50, then the difference means the sum of this clearance and this clearance. Both the clearances are same. So if you take this as C, 2C is equal to 0.5 mm. Correct? So 2C is equal to 0.5 mm. So C is nothing but 0.25 mm. Okay. So that's why I have written C as 0.25 mm, which is identical to 25 into 10 to the power minus 5 meters. You need to be a bit careful about these calculations. That's it. Okay. All of you are clear till this moment? Yes or no? So please tell me, are you all clear till this moment? Fine. Are you all clear till this moment? Do type in the chat box, guys. Fine. So look here. Let us go for the next question. So this is our next question. A journal bearing has a shaft diameter of 40 mm and a length of 40 mm. The shaft is rotating at 20 radians per second. Okay, and the viscosity of the lubricant is also given 20 megapascal per, millipascal second. The clearance is 0.020 mm. The loss of torque due to the viscosity of the lubricant. So just now we have seen the formula for power. This is the formula for power. You know, power is nothing but torque into angular velocity. So if you want to write the formula for torque, what will be the formula for torque? In this case, torque will be equal to, this is of course both are same cases, journal and bearing. So now if you divide this complete expression with omega, pi mu d cube L, pi mu d cube L omega by 4c. This is what you will be having for the torque, correct? So we have all the values. Let us collect the values. So the journal bearing has a shaft diameter of 40. So shaft diameter is d. That's what we are taking, 40 mm. So this can be written as 40 into 10 to the power minus 3 meters. Next, length of 40 mm. So length is also 40 mm because generally in journal bearings we take this d is equal to L. In your machine design course you will be able to see this anyhow. So this is meters. The shaft is rotating at 20 radians per second. So the angular velocity is also given 20 radians per second. Then the viscosity of the lubricant is 20 millipascal. So 20 into 10 to the power minus 3 millipascal. So this is pascal second. Fine. The clearance is 0.02 mm. So clearance is equal to 0.02 mm. That means this can be written as 2 into 10 to the power minus 5 meters. So we are writing everything in SI units. So the loss of torque due to viscosity. So they are asking you loss of torque due to viscosity. We have the value, pi is a constant anyhow. Mu value is given, d is given, L is given, omega is also given, clearance is also given. So can we identify this value? Can we identify this value? So let us do the calculation and let us identify. T is equal to pi times mu. What is the value of mu? 20 into 10 to the power minus 3 into d cube. What is the value of d cube? D is 4 into 10 to the power minus 2. So 4 cube into 10 to the power minus 6, which is 64 into 10 to the power minus 6 in meters. Okay, so d cube is meter cube, of course. Length L is given again 4 into 10 to the power minus 2 into omega. Omega is 20. So we have this 20 divided by 4 times of clearance. What is the clearance? 2 into 10 to the power minus 5. So let us perform this calculation. We'll get the answer. Okay, so let us perform this calculation. We can cancel this 10 to the power minus 2 and 10 to the power minus 3 and 10 to the power minus 5. Correct? So 2 4s are 8 and this cancels 64 and this is 8. So still we can cancel some things. Yes, we can definitely cancel. We can cancel these two zeros and we can write 10 to the power minus 4 here, and still we have something to cancel here. Yeah, I think these are the maximum calculations that we can perform. So T cancellations. So T is equal to 2 into 8, 16. 16 into 4, 64. 64 into 2, which is 128. Into, we have one pi, and pi into 10 to the power minus 4 Newton meters. Correct? This is the value we need to calculate. So 128 pi into 10 to the power minus 4. Let us calculate this. Let us calculate this. 128 into pi into 10 to the power minus 4 we can write. So that 10 to the power minus 4 can be written as power 10 of minus 4. This value gives you 0.040. So 0.040. Yeah, it's in option A. So 0.040. This is equal to 0.040 Newton meter. Okay, so that's what we have seen in option A, and you can also see the official gate key is also answer A. Fine. Yes. So are you all clear till this point? Did you all understand how I have taken this formula directly from the previous problem? Because both are journal bearing questions, but of course, you know, power is nothing but torque into angular velocity. So if you divide the power formula with angular velocity, you will get this torque. Correct? Subramanian, is that clear to all of you? Subramaniam, Akhil, Surendra, Jansi, Shubha, Bukya, all of you. Fine? Okay, let's go for the next question. So this is some next question. Oil in a hydraulic cylinder is compressed from an initial volume of 2 meter cube to 1.96 meter cube. If the pressure of the oil cylinder changes from 40 megapascals to 80 megapascals during compression, the bulk modulus of elasticity of the oil. So they are asking you for the bulk modulus of elasticity. And what is the formula of bulk modulus of elasticity that you have? E is equal to minus dP divided by dV by V. This is what we have the formula for bulk modulus, correct? So let us apply the things. E is equal to dP minus dP. dP is nothing but always final minus initial. So 80 megapascals minus 40 megapascals. So 40 into 40 into, okay, sorry, 80 minus 40, let us write this, 80 minus 40. And I think the answers are also in megapascals. Okay, fine. Let us leave in megapascals. Minus 80 minus 40 divided by, look carefully, delta V. dV is nothing but final minus initial, which is minus, 1.96 minus 2, and the initial value is 2, of course. So this is the value of the bulk modulus in megapascals. So let us calculate this value. First of all, minus 40 divided by 1.96 minus 2, which is minus 0.04, correct? So minus 0.04, and of course this 2 will get multiplied on the top. So this is minus 10 gets cancelled. 40 into 2 into this 4 here can be written as, of course, this 4 can be written as 4 into 10 to the power minus 2. So this cancels this 10 times, and we have 20, this 10 power minus 2, if it goes on to the top, we have 10 square megapascals, of course. So this is equal to 2000 megapascals. So 2000 megapascals is the bulk modulus of this fluid. So where is the 2000? Yes, here is the 2000. And what's the answer? Yes, this is B. Correct. So did you all understand? It's a simple definition that we have taught in the class. Young's modulus, this bulk modulus is nothing but minus of dP divided by dV by V. Correct? Can you all recollect this, which I have taught you in class? Since the options are in megapascals, I didn't disturb this value. I have written this in megapascals because this is meter cube, this is also meter cube. So this bottom term is dimensionless totally. Okay? Clear? Are you all clear till this point? Did you all understand how this is 2000 megapascals? It's just a basic definition of bulk modulus. Correct? Fine? Okay, very good. Let us go for the next problem. So there is some problem here. There is some pulley and this arrangements. A cubic block. Let us, okay, I hope all of you are fine, correct? Yes, all comments are fine here. Okay, good. A cubic block of side L. If this is a cubic block, look here. This is a cubic block. A cubic block of side L and mass capital M is dragged over an over an oil film across a table by a string connects to a hanging block of mass small m, as shown in the figure. So it's obvious there is a small block of mass m that is connected. So whenever this block is pulled down, then definitely this block which is here moves horizontally. Of course, given the dynamic, okay, let us see the question. The Newtonian oil film of thickness h. So this thickness is h, as it was mentioned, has dynamic viscosity mu. So there is some mu dynamic viscosity. H is the gap between this table and the oil. Yes, V in that formula is initial. Okay, V is always initial in general. So it has dynamic viscosity mu and the flow condition is laminar. So the acceleration due to gravity is g. The steady state velocity v of the block. What do you mean by steady state velocity? Which means this block here is not suffering any acceleration or deceleration. Correct? This block is moving at steady state velocity. If this is the case, if this block is moving at steady state velocity, then what do we have? See here. Whenever this block is moving under steady state, let us suppose this is the capital mass m that I am writing here. What are the forces that are acting on this block? If you try to attempt a free body diagram, so see here. Definitely there will be some force because of the tension in the string that's pulling this block, and also because of this contact, between fluid and solid, then we have some viscous force that will be acting also in the opposite direction. Correct? So basically we have this tension in the string and also some viscous force that is acting. Now let us try to draw the free body diagram of this. If this block is not under any acceleration and if the string length is constant, then will there be any acceleration in this block m? Please tell me. Whenever this block is moving at some steady state velocity, and if this block is moving at steady state velocity, and if the length of the string is constant, then definitely will there be any acceleration in the small block small m? Will there be any acceleration in this small block small m of mass small m? So please do type in the chat box, students. Will there be any acceleration in this small block? No. Correct? There won't be any acceleration in this small block. Correct. Which means you can see clearly if you try to draw the free body diagram of this block of mass small m, then this block has two forces acting, of course. So there is some weight of the block and also there is some tension. Correct? These are the only two forces on this block, of course. So now this is tension and this is equal to mg. So this is the case. So which means if this block has to be in equilibrium, if you write sigma Fy is equal to 0, then one thing is clear, this T should be equal to mg. Yes, so let us replace this T here with mg. Or else, if you write for the equilibrium, we have T is equal to Fv, viscous force, which means your mg is equal to, what is the viscous force now? You can apply Newton's law of viscosity, mu into u by v, I mean velocity gradient. So if you see there is a linear velocity gradient, of course, because we are doing Newtonian approach, so we can write the velocity profile, velocity gradient as v minus 0 divided by this v velocity gradient is occurring within a distance of h, so h into this is shear stress, but what we are dealing with, we are dealing with force. So we need to multiply this with the area which is in common or in contact with, or the area of the solid that is in contact with the fluid, correct? So if this is a cubic block of side L, then what will be the area that is in contact? Definitely L square, correct? This is what we will be having, because area of each face will be L square and one face will be in contact with the liquid. So if you calculate the expression for V from this, because they are asking you for the steady state velocity V is equal to small m g h divided by mu L square. This is the formula for the steady state velocity which is happening here. So that's given in option C exactly. Small m g h divided by mu L square, and you can see clearly here the answer is also C in the official gate key. Is that clear to all of you? This is a very simple question. Of course, you need a little knowledge on mechanics. That's it. Clear? Did you all understand how this is option C then? B is equal to mgh, of course, small m divided by mu L square. And you can see carefully, my friends, in the first option it's given capital M, because if you confuse between small m and capital N, many of you will be seeing the first option and you will take the first option, but which is a wrong answer in general. Okay, so when marking your options, please be a bit careful, especially with the questions involving options. Okay, fine. So all of you are clear? Ranjita, Jansi, Shubha, Akhil, Suyendra, Subramanian and all. Bukya Veyanna. Is that clear to all of you? I hope things are fine. Let us go for the next problem. Okay, there is some theoretical question. For a Newtonian fluid, shear stress is proportional to shear strain. Rate of shear stress is proportional to shear strain. Shear stress is proportional to rate of shear strain, and rate of shear stress is proportional to rate of shear strain. What does Newton's law of viscosity tells us? For a Newtonian fluid, what is a Newtonian fluid? Basically, any fluid which obeys or satisfies. Suyendra, you have some question? Okay, I'll get back after this question. Look, for a Newtonian fluid, what is a Newtonian fluid generally? Newtonian fluid is something which obeys Newton's laws of viscosity. And I clearly told you, Newton's laws of viscosity is nothing but your shear stress acting on any layer is proportional to the rate of shear strain, correct? This is what we have seen here. So shear stress, this is shear stress that's acting, and of course this is, if phi is the shear strain, then this is rate of shear strain. This is a simple question, correct? So this is the rate of shear strain, correct? So this is the case. So C is the correct answer. Shear stress is proportional to rate of shear strain. C is the correct answer. Yes. Why we have not considered mass of the block? Shubha, because I'll tell you clearly. This block has its mass, and of course this weight m into g acts in the vertical direction, but of course we are dealing the balance of forces in the horizontal direction. So since this weight is acting in the vertical direction, we are not considering this force for our analysis, because sigma fx is equal to 0 in whenever your horizontal velocity is constant. So sigma fx is equal to 0 implies this we will consider only this forces T and viscous force, but not this vertical force mg. Okay, this is the reason. And of course, Suyendra, you are also asking something. Explain about steady state in the question. Steady state means the velocity of the block is not changing with respect to time, which means the block doesn't suffer any acceleration, either convective or of course this is the solid, so you can just term it as acceleration. So generally this block is not suffering any acceleration, because acceleration is nothing but dv by dt, and whenever this is time independent, your velocity has to be constant. This has to be 0 in case of a steady state, which means your velocity has to be constant. Okay, so this is the reason of steady state in the question. Clear? Yes, I hope all of you are clear. Even the correct answer is C. This is a simple question, you know this, correct? So shear stress is proportional to the rate of shear strain. Fine. So let us go for the next question. There is one question. An incompressible fluid of kinematic viscosity is equal to 7.4 into 10 to the power minus 7 meters per second. Specific gravity 0.88 is held between two parallel plates. If the top plate is moved with a velocity of 0.5 meters per second, while the bottom one is held stationary. Okay. So again, this is the same case that we are dealing with. There are two plates, and of course, the bottom one is fixed. The bottom one is fixed, and the top one is being moved at a velocity of v is equal to, how much is this? 0.5 meters per second square. So 1/2 meters per second. We know this, correct? And of course, the fluid attains a linear velocity profile in the gap of 0.5 mm between the plates. So this gap is 0.5 mm. This gap is 0.5 mm, and there is some linear velocity profile, correct? This is what it's given in the question. You can see the fluid attains a linear velocity profile in the gap of 0.5 mm. So this is what you can write. So we can see if this is your reference axis for velocity, then there is some linear velocity profile. Fine. This is the case, correct? So we can apply what they are asking you finally, the shear stress in Pascal on the surface of the bottom plate. So they are asking you what is the shear stress value at this point, correct? So we know tau is equal to mu into, they are asking you this shear stress at the point y is equal to 0, and since mu is equal to constant, we will consider this du by dy at y is equal to 0. But here the velocity is varying linearly, which means your velocity gradient is same at every point. So in general, if you write mu into du by dy. So for linear velocity profiles, we can write this velocity is 1/2, and here its velocity is 0. V is equal to 0. So velocity gradient, we can write this as 1/2 minus 0 divided by this clearance. This is in mm. Let us convert this into SI units. So 5 into 10 to the power minus 4 meters. And what about dynamic viscosity? It's given. Kinematic viscosity is given, and also specific gravity of the fluid is given, 0.88, which means, can I write this dynamic viscosity? You know, we have this kinematic viscosity, nu is equal to mu by rho. So what can we write for dynamic viscosity? Nu times density, correct? And here it's given specific gravity. So how you will get this density? Nu into specific gravity of the fluid into the reference density, which is density of water, correct? So this can be written as mu is equal to kinematic viscosity, which is 7.4 into, or let us write 7.4 into 10 to the power minus 7 into 1/2 divided by the clearance is 5 into 10 to the power minus 4, or the gap between the plates, into this. Okay, the kinematic viscosity is not yet done. Okay, this is kinematic viscosity. So if you want dynamic viscosity, 0.88 into density of water is 1000. So this density is nothing but 8 into this thing. So density into kinematic viscosity is your dynamic viscosity divided by 1/2 divided by, and 5 into 10 to the power minus 4. 5 into 10 to the power minus 4. This is what we have here, correct? So you can do one thing. You can cancel this 10 to the power minus 4 and this 10 to the power minus 7. You have 10 to the power minus 3 here, and of course this 2, if it comes in the denominator, this 2 into 5 will be 10, and you can cancel 1 0 as well. So 88 into 7.4. 7.4 into 88. In pascals, this is in pascals, so 7.4 into 88. If you use your virtual calculator, 88 into 7.4, this will give you 651.2. So 651.2 pascals. Do we have that in options? Okay, into 10 to the power minus 3 is also available, correct? So into 10 to the power minus 3 is also available here. So 88 into 10 to the power minus 3. So this is 10 to the power minus 3 of this complete value. So 0.651. 0.651 pascals. Correct? So this is in option B, and of course answer B is correct in this case. Yes. 0.651 pascals, which is in option B, is the correct answer in this case. Yes, B is correct answer, because we have 10 to the power minus 3 in these cancellations that is left over. Okay, fine. Let us go for the next question quickly. The SI unit of kinematic viscosity nu is. So what is the SI unit? I told you clearly, in case of kinematic viscosity, SI units and MKS units both are same. So kinematic viscosity is nothing but mu by rho. I have already shown this for you in class. So let me show that once again. So mu units are nothing but Newton second per meter square, and the units of density are kg per meter cube. So if you see carefully, the units of Newton are kg meter per second square into second divided by meter square into kg per meter cube. So you can write this meter cube here. Correct? So if you make the simplifications, this meter square cancels this meter cube 1 meter times, and this second cancels this square, and of course this kg cancels this kg. So meter into meter is meter square per second. Correct? And also you can see this from its previous question, you can see meter square per second is the SI unit of kinematic viscosity. Correct? So meter square per second, option A directly, which we have stated. Yes, correct answer is A, meter square per second. Okay, so let us go for the next question. If P is the gauge pressure between a spherical, is the gauge pressure within a spherical droplet, it's clearly given it's a spherical droplet. So there is some drop. This is P in at this point and this is P out. Okay, so there is the gauge pressure difference P within a spherical droplet, the gauge pressure within the bubble of same fluid and of same size. So this is droplet. In case of droplet, we know, in case of droplet, delta P of droplet will be equal to sigma into 2 by r. So 2 sigma by r basically. Next, delta P of bubble, this will be equal to 4 sigma by r. So it's clearly given the gauge pressure within the bubble of same fluid. If this is same fluid, then definitely this sigma is same in both the cases and of same size, which means this r will also be same. Correct? So this implies your delta P of droplet is nothing but half of delta P within bubble. And you can see clearly, so they are asking you for bubble. So delta P of bubble is nothing but 2 times of delta of droplet, and you can see clearly if P is the gauge pressure between gauge pressure within a spherical droplet. So P is the difference in case of droplet, so 2 times of P will be the difference in case of bubble. So delta P within the bubble, or the gauge pressure difference within the bubble, will be 2 times of P, which you can see here in option D. Yes, D is the correct answer in this case. Answer D. Are you all clear? Are you all getting the idea on solving these problems? We have already solved some 12 problems. Let us solve some more problems. Okay. So are you all clear till this point? Are you all clear till this point? Yes? Very good. I hope all of you are clear till this point. Yes? Fine. Let us go for the next problem. Kinematic viscosity of air at 20 degrees Celsius is given to be 1.6 into 10 to the power minus 5 meters per second, meter square per second. So kinematic viscosity at 20 degrees Celsius, this is given as 1.6 into 10 to the power minus 5 meter square per second. Then its kinematic viscosity at 70 degrees Celsius will be varying approximately. So kinematic viscosity at 70 degrees Celsius, this is what they are asking, and I think they have given some gas is given. Okay. So what will be this value? This is what they are asking. I told you clearly for gases, and of course air can be treated as an ideal gas. I told you this mu means this dynamic viscosity will be proportional to square root of T, and your density will be proportional to 1 by T. Okay. So I told you this kinematic viscosity will be proportional to T to the power 3 by 2, but of course this T has to be absolute in all the cases. Correct? So this is what I told you. So can you all recollect this? I told you. So nu will be equal to T absolute whole power 3 by 2. If that's the case, then you can write mu at 20 degrees Celsius divided by nu at 70 degrees Celsius. This will be equal to, since we are taking 2 different values, and if you remove this proportionality sign, so T absolute at 20, which is 293, divided by T absolute at 70. So 273 plus 70, which is 343, whole to the power 3 by 2. So which means if you want to have this value of nu at 70 degrees Celsius, this will be equal to 293 by 343. Okay, at 70, correct? So if this goes up, so 343 divided by 273 whole 293 whole to the power 3 by 2 into kinematic viscosity at 20 degrees Celsius. This is the value. So let us calculate this value and let us see how much is the value. 343 divided by 293 whole to the power 1.5. 3 by 2 is nothing but 1.5. So this into, what is the kinematic viscosity given? Since the answers are also in 10 power minus 5, let us multiply 1.6 alone. Okay. So into 1.6. So if you see 2.026. So this value is nothing but kinematic viscosity at 70 degrees Celsius is nothing but 2.026 into 10 to the power minus 5 meter square per second. And you can see clearly this value is in option A. Yes. So yes, this is in answer A also. Fine. Clear? So A is the correct answer. 2.02 into 10 to the power minus 5. Look, one thing is very clear. You can eliminate two options because this value means the kinematic viscosity value will be definitely more than 1.6, correct? So 1.6 and 1.2 won't be the answers. You can eliminate these two, and anyhow you can identify that answer is lying within 1 and C. But of course, since you can calculate this easily, you can always write 2.02 into 10 to the power minus 5 meter square per second in this. Okay. The only thing that need to be remembered here in this case is this formulation. Okay. So fine. Is that clear to all of you? Is that clear to all of you? Clear? So please do type in the chat box. Is that clear to all of you? Yes. So let us go for the next part. The dimension of surface tension is, this is a very easy question. You need to answer this. Okay. So please answer. Please do type in the chat box. The dimensions of surface tension. Of course, the units is what they mean, because if you look at the options, they mean the units of surface tension. So please tell me what is the correct answer in this case. And whoever is on live, please do respond for all the questions. Okay. So please do respond. Please do type in the chat box. Fine. What is the answer for this question? I'm waiting for your comments in the chat box. Okay. So please do type in the chat box. What are the answers? C. Is it joule per meter square? Is that the correct answer? Yes. Yes. Because I told you the surface tension is nothing but force divided by the length. Of course, what is force, what is length, we have seen in yesterday's class. So these units are nothing but Newton per meter. But if you see carefully, there is no option involving Newton per meter. So if you multiply a meter on all the sides, means on numerator and denominator, then you have Newton meter divided by meter square. And this Newton meter is nothing but force into displacement, which can be written as joule per meter square, which is in option C. Correct. So C is the correct answer. Yes. Okay. So C is the correct answer. So you can see the official key is also C. Let's go for the next question. The dimension of surface tension. This is also a very easy question. So see carefully. They are asking for the dimension of surface tension. We did this. So surface tension is nothing but force per length, and force is nothing but mass into acceleration. So m times, or m, if you write in terms of MLT units, so mass into acceleration is nothing but meters per second square. So meters is L, and seconds per second square is nothing but t to the power minus 2 divided by the fundamental dimensions of length is nothing but L. So if you cancel the things, so if you cancel few things, you have mt to the power minus 2 is the dimension of the surface tension. Okay. So mt to the power minus 2, which is in option D. Okay. Are you all clear till this point? Yes or no? So please do type. Are you all clear till this point? Are you all clear? Yes. So D is the correct answer. Fine. Let us go for the next question. They are asking something. A fluid is one which can be defined as a substance that has the same shear stress at all points, can deform indefinitely under the action of the smallest shear force, has the small shear force in all, has the small shear stress in all directions is practically incompressible. So please tell me, what is a fluid? What is the basic definition of fluid I have given you? What is the basic definition of fluid that I have given you? So please tell me, what is the basic definition of fluid that I gave you? Fluid is nothing but that can deform indefinitely under the action of the small shear force, correct? This is what we have given you, and of course this is the definition of fluid. The fluid has the same shear stress at all points. No, this need not happen because the fluid can be in static state. Then coming to option C, has the small shear stress in all directions. No, a static fluid never suffers any shear stress. Okay, it is practically incompressible. Never. Fluids means both liquids and gases as well. Liquids are practically incompressible. Yes, I agree. But if there is liquid here, then this option D is definitely correct. Yes, I agree. But there is something called fluid, and fluids do include gases in them, and gases are practically compressible. Okay, so because of this term fluid here, you can't put this option D. Is that clear to all of you? So yes, I'm happy that all of you are writing correct. Vanchita, Jansi, Shubha, Akhil, Suyendra and all. Yeah, fine. So let us go for this next question. Group 1 contains the types of fluid which, while group 2 contains the shear stress rate of group 2 contains the shear stress rate of shear relationship of different types of fluids as shown in the figure. Okay. So group 1, group 2, the correct match between group 1 and group 2 is dash. Look, when solving these kind of questions, I'll tell you something. When solving such questions, the main thing that you need to identify is, look, here all the P's are 2. Means if you keep on checking P, then there won't be any use. If you check Q, there are 2 options of Q which are same. So there is no use. But if you see, yes, there are different for all the options, correct? So if you can identify what is the correct identification of this dilatant fluid, then your answer will get in a shorter time in exam, correct? So this is what you can always identify. Means if you check what is the correct relation of yes, you'll get only one correct option. So let us check that. What is this dilatant fluid? Dilatant fluids are generally called shear thickening fluids. And you know, if this is your Newtonian fluid, I have given you this chart, correct? Then this will be your dilatant fluid. And this is your pseudoplastic fluid, correct? Pseudoplastic fluid. And of course, I have also given you one thing, which is the plastic fluid. This is something plastic fluid, correct? These are called viscoelastic fluids, and we have ideal Bingham, aphectic, thixotrophic and all. So all those are plastic fluids. So this is the chart that I gave you. Means of course I have given you 2 extra fluids also. This is ideal Bingham and this is the aphectic as well, correct? But of course, for the time being, this is the chart that's given. So yes means the dilatant fluid is nothing but this curve 3. So curve 3 is for dilatant. So S3 is here. So this is the correct answer, C. And you can see the official gate key is also C. So basically this is rate of shear, which is du by dy in our case, and of course this is yield shear stress. Okay, this is tau y and that is tau axis. Okay, we have seen this diagram. Which can't resist shear stress? A fluid in static state cannot resist shear stress. Okay, because as soon as you apply infinitesimally small shear stress, the fluid starts moving. Okay, that's the reason. Okay, Vamsi, I'll try to do that because today, even for past 2 days, I was searching the comprehensive mathematics notes, but I couldn't find it in the television, this smart board or some other places. But definitely I'll show you the, then thermodynamics will also not be available, I guess. Okay. But I think since many of you are in common groups like engineers of mechanical channel, mathematics channel, and also if some of you have the notes, please do share among yourself. Okay. Yes, this is a question from GATE. Okay, I'm not dealing ESC questions, Akhil. All these are GATE questions, and you can see a few questions here. Next, something is given, the dimensions of kinematic viscosity. So the dimensions for kinematic viscosity, you have seen the units, SI units of kinematic viscosity are meter square per second. So this is nothing but dimensionally, dimensions of meter square is nothing but L square, and dimensions of second is nothing but time. So L square T to the power minus 1 is the dimensions of kinematic viscosity. Okay, so L square T to the power minus 1. Where it is? It's in option C. L square by T. So C is the correct answer in this case. Yeah, last class notes definitely I'll send you, Suyendra, no issue. I think I've shared it in the Telegram group already, but if not the case, I'll definitely shear you, because daily we are shearing. Okay, so let us go for the next question quickly. The necessary and sufficient condition for a surface to be called as free surface. What is a free surface? Yesterday when defining, of course, even when defining fluid, I have told you this, and also during surface tension, I have told you this. What is a free surface? What is a free surface? Shear stress acting on it must be 0, correct? Yes, because I told you no shear stress should be acting, no stress should be acting on it. Look, if this is your surface, if this is your surface, then definitely at this point there will be some tensile stress because of the surrounding molecules, correct? But if this has to be a free surface and if this has to be stationary, then definitely shear stress should not be there on the surface, correct? No stress should be acting on it. No, there will be some tensile stress. So this is wrong. Tensile stress acting on it must be 0. Need not be because of the surface tension forces, correct? No point on it should be under any stress. No, every point on the surface is under tensile stress. So this point is also wrong, but this shear stress should not be there. Okay, there should be only purely tensile stress on the surface, and that's why because of that we have some surface tension forces. Okay, so C is the correct answer in this case. Yes, so C is the correct answer because we have some surface tension forces even in a static liquid. I mean, even on a free surface. Okay, fine. Are you all clear till this? Then let us go for the next question quickly. The unit of dynamic viscosity of a fluid. What are the units of a dynamic viscosity of fluid? Dynamic viscosity of fluid is nothing but your mu. And what are the units of mu? Pascal second. SI units of mu is nothing but Pascal second. And is Pascal second given anywhere directly? This is definitely wrong because Pascal second per meter square is not the answer. So this is nothing but Pascal second. Okay, this is also not, this is Newton second per meter square. Yes, then this is definitely Pascal second, correct? Because this Newton per meter square is nothing but Pascals and this is Pascal second. Correct? So what's the answer? B. B is the correct answer. Yes. And of course, this will be wrong because kg per meter second is the correct unit. And meter square per second is the unit of kinematic viscosity, but it's clearly given this should be dynamic viscosity. Okay? Yes. So B is the correct answer. Newton second per meter square. All these are previous gate questions, but of course simple questions. Okay? So read this. With increase of temperature, dynamic viscosity of a fluid. What happens to dynamic viscosity of a fluid? Read the options and tell me the answer. I'll give you some time. So please, read the things and tell me the answer. So explain 19th once. Okay, I'll explain. Yes, 19th. If this is a free surface, then definitely there acts some surface tension forces on this, correct? So it's not like no stress will be acting on it. No, this option is wrong because at every point on the surface there will be some surface tension force that is acting. Okay, so that's why option A is wrong. So tensile stress acting on it must be 0, need not be, because even though there is a tensile stress that if at this point if you have some tensile stress at this point, then definitely you have some other tensile stress at this, tensile force pulling at the other end also. So this won't be the option. But of course, if you take about option D, no point on it should be under any stress. No, on every point on the free surface there will be some surface tension force. Actually, first option and last option are identical. Okay, and C is the correct answer because for a fluid layer to be static, then definitely for a fluid layer to be static, definitely shear stress acting on that should be 0. Okay, so next 21. Yes, with increase of temperature, the dynamic viscosity of the fluid. This term has to be made a note. If it's given liquid, then definitely decreases is the correct answer. And I think one of these options should be decreasing. Okay, one should be decreasing because both options can't be same. So one option out of these two will be increases and other option will be decreases. So increases if the fluid is gas and decreases if it is a liquid. This is correct because we have seen mu of liquid is inversely proportional to temperature. Correct? This is what we have seen. So as temperature increases, your dynamic viscosity of the liquid decreases. And of course, this is not exactly like this. It's something like exponential, roughly exponential, which I have told you in the last class, roughly exponential. And What about dynamic viscosity of gases? If this is a gas, then this is proportional to square root of T absolute. Okay, this is what we have seen. So this is what we have seen. So mu gas is proportional to T absolute. So in case of liquids, this viscosity decreases as your temperature increases, and in case of gases, this increases. So this is what the correct option that can suit, because fluid means they mean both liquid and gas. So D is the correct option. Yes, as told by you. Jansi, it's not B, because if the fluid can also be a liquid. Okay, so with increase in temperature, there can be some decrease in viscosity also for liquids. Okay, so that's the reason. So even the official key is D. So let's go for the next question. A liquid of density rho and dynamic viscosity mu flows steadily down an inclined plane in a thin sheet of constant thickness T. Look here. So basically we have some inclined plane. So on this inclined plane, let me plot this a bit neatly. So we have some inclined plane, something like this. Okay. A liquid of density rho and dynamic viscosity mu flows steadily down an inclined plane. So there is some liquid of dynamic viscosity mu. So the dynamic viscosity of this liquid is given. So the dynamic viscosity is mu, and the liquid itself is falling now in a thin sheet of constant thickness T. So this sheet thickness is T, means this liquid has always some constant thickness T. This is theta, of course. Okay. Then neglecting air friction, the shear stress on the bottom surface due to the liquid flow, where theta is the angle the plane makes with the horizontal. So this is theta, this is mu, and this is T, and they have also mentioned a liquid of density rho and dynamic viscosity mu. So this density of this liquid is delta, rho. Okay, this is what we have, and let us suppose this length of the liquid which is flowing is L for the time being. Okay, and that's thickness. So if this is the case, then if the liquid is flowing, then they are asking you what is the shear stress acting on the bottom surface due to the liquid flow. So shear stress acting on the bottom layer, definitely there will be some viscous effects, and let us suppose when this liquid is moving like this, there are two forces, the weight of the liquid which is acting like this, and also there is some viscous force to its own flow which is acting on the upward direction. Correct? So which means if you take the liquid alone, if this is your liquid which you are having, then definitely there will be some weight of the liquid that's acting vertically downwards, and because of this there will be some components. Okay, and perpendicular to the plane. Let us suppose these are the components, and also you will be having some viscous force that's acting. Correct? So this will be your viscous force. So if you see, this is weight of the liquid and this is your viscous force, and this viscous force is nothing but shear stress divided by area. So let us try to identify this. If this is moving at steady state, then this should be equal to, this weight should be equal to Fv. Correct? So W sin theta should be equal to Fv. Correct? Viscous force. And what about W? W is nothing but density of the fluid into volume. Volume is nothing but this thickness into cross section area which is perpendicular to this plane. Correct? If let us suppose this liquid film is coming out of the board for 5 centimeters, then this, let us suppose if this is the liquid layer, then this cross section area which is my hand is the total volume of the liquid. So T into this area, let us suppose A, into gravity into sin theta. This should be equal to your viscous force divided into, and viscous force is nothing but shear stress into area. So tau into area. This is what we write here. Correct? So tau into area. So area gets cancelled. So the shear stress that's acting is equal to rho Tg sin theta. Correct? So rho Gt sin theta. Okay, so A is the correct option here. So the shear stress that's acting on the bottommost layer is equal to rho Tg sin theta. So A is the correct answer. Okay, so A is the correct answer in this case, because weight of the fluid should be balanced by viscous force, and a component of this, actually in this direction this force has to be balanced by this viscous force. So W, if this angle is theta, then definitely this angle will be W sin theta. Okay, let us identify properly. So if this angle is theta, then definitely this angle, this component will be W sin theta, and this will be W cos theta. Correct? So your W sin theta should be equal to viscous force, and viscous force is nothing but shear stress acting on the layer into the area of this fluid solid, liquid solid contact. Okay. So I hope all of you are clear till this point. From the next time, I'll make the slides when I'm taking a class on the app. I make sure that the slide will be a little right towards us so that you can see complete question. Okay. So are you all clear? So please tell me, Jansi, Suyendra, Subramanian, Shubha, Akil. Are you all clear till this point? Yes? Okay. Chalo, it's I think it's 11 o'clock already, so fine. Let us go for 2 more questions and let us end the show. I mean, let us take some 25 questions and let us end the show. Shear stress develops on a fluid element if the fluid. So please tell me, shear stress develops on a fluid element if the fluid. Look, let us take options individually. Is that rest? Is this possible? No, because if the fluid is at rest, then there won't be any shear stress acting on any layer. Next, if the container is subjected to uniform linear acceleration. Look, whenever the container is subjected to uniform linear acceleration, there will be some acceleration of the fluid, but of course, depending on this acceleration, the fluid gets settled like this. We'll see in fluid kinematics why this is happening. Okay. They are not generally in this format. Whenever this is accelerating, you will get the opposite pattern. Okay. I'm sorry for this. So if your fluid container is accelerating in this direction, then your liquid gets settled like this. I will show you in chapter number 3, fluid kinematics, why this happens. Okay. I think I named it chapter number 5. Okay, fine. In chapter number 5, I will show you. But there won't be any relative motion between the layers. Okay. Means if you take any 2 layers of fluid at any instant, then definitely there won't be any relative motion between the fluid layers. So there won't be any shear stress that will be acting here. Okay. So there won't be any shear stress acting on this case. So this is also wrong because it's subjected to uniform linear acceleration, which means there won't be any relative motion between the fluid layers. Also, it's inviscid. Inviscid means viscosity is 0, and tau is equal to nu into du by dy generally. So whenever the fluid is inviscid, means if the viscosity is 0, then definitely there won't be any shear stress that's acting. So this is also wrong, but this is correct. Is viscous and the flow is non-uniform. So generally, if there is some flow which is non-uniform, means if the layers of velocity is different, means if the velocity is different at different layers, that's what we mean with non-uniformity. And if this is the case, then definitely if the fluid is also having some viscosity, then there is also some mu and there is also some du by dy. So there exists some shear stress definitely within the fluid. So your D is the correct answer. Okay. In case of linear acceleration, there won't be any shear stress because the fluid layers won't have a relative motion between them. They are fixed in a container and they can't, move. Means there can't be any fluid motion between the layers. There can't be any relative motion between the fluid layers in general. Okay. So we'll solve this question and one more question and we'll end up this class. Okay. And tomorrow we'll deal one last lecture of this first module, capillarity. So after this capillarity, we'll go into the second chapter, fluid statics. Okay. So tomorrow again at 9:30 to 11 p.m. But the class is on YouTube. Okay. The class is on YouTube. So from 9:30 to 11 p.m. you'll be having class on YouTube on the topic of capillarity, and that's the last lecture of the first module. Okay. So please don't miss that because there are a few good questions even on capillarity, but I have covered only till surface tension. I have put the questions only till surface tension. So on next Saturday, again when we are having some problem solving session, I'll put few questions of capillarity and also some questions on fluid statics, which we'll cover from Tuesday to Friday. Is that clear to all of you? Is that clear to all of you? Fine. So let us try to attempt this. The variation of shear stress tau, again is shear strain weight, du by dy is given in the figure. Identify the line or curve among P, Q and RS that represents an ideal fluid. What is the meaning of ideal fluid? What is the meaning of ideal fluid? I told you clearly, ideal fluid is nothing but the fluid which is incompressible and also inviscid. Incompressible and also inviscid, correct? So the fluid means basically it doesn't have any dynamic viscosity and also this density remains constant, correct, of the fluid. So I told you clearly on that day, this line P corresponds to ideal fluid. Yes, and this line corresponds to ideal solid. And of course, these are dilatant, and of course, this is for pseudoplastic fluids. Correct? We have discussed all these things in detail. So definitely your correct answer is that represents an ideal fluid is this curve. So P is the fluid which is ideal. We'll solve one last question and we'll move. We'll end up this class. Okay. So one last question we'll do and we'll end up this class. Clear? Okay, there is some question. 25 questions, let us complete. Consider the two-dimensional laminar flow of water. Mu is equal to 0.001 Newton second per meter square. So the dynamic viscosity is given, which is 0.001 Newton second per meter square. Correct? So this can be written as 10 to the power minus 3 Newton second per meter square. Okay. Then between two infinitely long plates 0.1 meter apart. So this distance is 0.1, which you can see. So if I call this as my clearance C, so the gap between the plates H, for example, then H is equal to 0.1 meter, which is 10 to the power minus 1 meter. Fine. And we also have the velocity profile at any location is given by u of y is equal to 100 times of 0.1 y minus y square. So u of y is given as a function 100 times of 0.1 y minus y square. Okay. Where meters per second, where y is in meters, of course. The magnitude of the shear stress rounded off to 2 decimal places acting on the bottom plate is. So this is the bottom plate. So they are asking you the shear stress at this location. And if this is your y-axis and if this is the horizon, that means they are asking you tau at y is equal to 0, which means you can write mu into du by dy at y is equal to 0. Why we can write this? Because it's clearly given. Okay, so velocity profile is given. So mu into du by dy at y is equal to 0. So mu value is 10 to the power minus 3 into what is the value of du by dy? If this is your y, if you calculate du by dy in this case, 100 is the constant into the differentiation of this is 0.1 minus 2y. Correct? So this value means 100 times into 0.1 minus 2y at y is equal to 0. This is what we can write. So 100 into 10 to the power minus 3 will give you 10 to the power minus 1. So if you put y is equal to 0, you have 0.1 here. So 0.1 into 10 to the power minus 1. 0.1 into 10 to the power minus 1. What is the value? 0.1 into 10 to the power minus 1. So 0.01 pascals. Shear stress we are talking about. So 0.01 pascals, and pascals is nothing but Newton per meter square. So 0.01 is the correct answer in this case. Okay. Clear? So we have 6 more questions, but of course I am giving you these 6 more questions for practice because those are pretty much easy questions. So we'll stop this lecture here, and as I told you, tomorrow we have this last lecture on the first module, lecture number 6 on concept of capillarity, and this will be the last concluding lecture on fluid properties. Okay, so please don't miss this lecture. And also, as I told you, we have started offline batch. So tomorrow again we have a class on Sunday for the regular weekend as well. So we have already started one batch on 1st of March, which is running successfully. So we are having second batch from 15th of March, and finally the last batch on 29th of March. Okay, so please don't miss the sessions. And of course, if you join, then definitely your class will be from 2 p.m. to 7 p.m. daily, and this batch generally goes for 5 to 6 months. Okay, and this is an offline batch. Okay, and you can see all the faculties that are teaching at EH will be of this level, at which you are getting this free content. So please don't miss. If they ask top plate is also same answer, no surrender. Then in place of y is equal to 0, you need to substitute. Let me take out that question. So in place of, I have substituted y is equal to 0, but if this is top plate, then this is at y is equal to 0.1. So instead of 0 here, you will write 0.1, and finally in place of this y, you will substitute 0.1 and you will get the answer. Okay. So as I was telling you, so this is the regular batch timings and the duration generally which we deal with. And of course, this is our classroom which I have shown you a lot of times, and one more time again. So here you can definitely find some of your seat if you would like to join and get trained with us. Okay. And also these are the official links of official details of Engineers Hub. You can always get some free content that could benefit you from the YouTube channel of Engineers Hub. Even today there's this session by IIT Bombay alumnus have been done. So I hope that you have got some useful information, and this is the official Telegram channel of Engineers Hub Mechanical, where we are posting the notes on daily basis. And also this is some other channel for all others like ECE, Triple E, Civil Engineering, Computer Science and others. So we are posting notes on both these channels because keeping in mind that there are a few civil engineering and chemical students as well in this group. And this is official Twitter account of Engineers Hub, engineers_hub, and this is the official Facebook page, LinkedIn and official website of Engineers Hub where you can get all the enough data on this. Is that clear to all of you? Is that clear to all of you? So please do respond. Please do type in the chat box. Is that clear to all of you? Is that clear to all of you? I hope you are enjoying the class on the app, but of course the little issue of this the screen getting a bit restricted will get resolved next time. No issue. Next time when I make the questions here, I'll make sure that you can see the complete question clearly. Okay. Is that clear? Yeah, I think you can see the things. Okay. So next class is at 9:30 p.m. tomorrow, and please don't miss the class. That will be the concluding lecture on the fluid statics. Fluid and its properties. So immediately after that, we'll start fluid statics. Okay. That lecture is on Monday. So tomorrow, I'm sorry if I'm telling tomorrow. Tomorrow is a Sunday. We don't have any class. As I told you, we'll be having 6 classes a week. Of course, 1 class is for tutorials, means for solving some problems on every Saturday, and 5 active lectures for theory. Okay. So that's on Monday. Next class is on Monday, and that class is on YouTube again. It's on YouTube because I don't want to make others to miss some content. So content what we are doing, we'll post it on YouTube. But of course, problems, since you are paying some extra effort like installing the app and coming to this class, I want to do problem solving sessions on app. And please remember, how well you know theory is equally important as how better you know how to solve problems. Okay. So we'll do such way. 1 class every week, we'll be having it on app for problem solving. Clear? Then I hope everything is clear from my side. We'll meet on Monday at 9:30 p.m. sharp on YouTube channel of Engineers Hub. Okay. Thank you all. Good night. Have a nice weekend.